So welcome everyone to the TUT Distinguished Lecture Series. The TUT Distinguished Lecture Series was launched by the Department of Combinatorics and Optimization in 2017 in honor of William Tutt's centenary birthday. Since then, it has featured leading researchers in the areas of mathematics that are represented in our department. And it's a pleasure to have Ryan O'Donnell speak in the series. Ryan completed his BSc in Mathematics and Computer Science at University of Toronto and his PhD in the Department of Applied Mathematics at MIT. After holding postdoctoral positions at the Institute for Advanced Study and Microsoft Research, he joined Carnegie Mellon University, where he's a professor of computer science. It's quite hard, at least for me, to characterize Ryan's research. It spans a wide range of areas within mathematics and computer science, including approximability of optimization problems, learning theory, and more recently, quantum computation. He's known for showing the optimality of the Goemans-Williamson algorithm for approximating max cut. Assuming the unique games conjecture. He participated in the first polymath project, Polymath 1, for developing a combinatorial proof of the density-Hales-Jewett theorem. He's an author, or the author, of the book Analysis of Boolean Functions from Cambridge University Press. Within quantum computation, he's known for his contributions to several different areas, including optimal algorithms for learning quantum states, also known as state tomography, and for the first construction of quantum LDPC codes that break the square root distance barrier. Ryan has received several accolades: the NSF Career Award, a Sloan Fellowship, a Herbert A. Simon Award for Teaching Excellence from CMU, and Best Paper and Best Student Paper Awards at the Conference on Computational Complexity. In 2014, he was invited to speak at the International Congress of Mathematicians. Ryan has served as editor-in-chief of ACM Transactions on Computation Theory, an editor of SIAM Journal on Discrete Mathematics, and the journal Theory of Computing. He was the program committee chair for the 2024 edition of the Symposium on Theory of Computing. He was, or currently is, on the scientific advisory bodies of several institutes, Mathematics Science Research Institute, as it was formerly known, currently SLM ATH, and the Simons Institute for the Theory of Computing, and on the scientific board of the Electronic Colloquium on Computational Complexity. Ryan also maintains a YouTube channel that you might have come across with lectures from his courses, on his own research, as well as on other areas of theoretical computer science. I've enjoyed it immensely, and I highly recommend it, and I expect you'll see a sampling of it today. Please join me in welcoming Ryan.
Thanks so much, Ashwin, for that kind introduction. It's great to be here. Thanks for being here on Friday in August. So this is a paper I wrote recently about a quantum speedup for a classical problem. And let me start by saying that, this paper is heavily based on an earlier paper by Matt Hastings. It's a great paper. Really, we just studied his paper really hard, and this result is kind of a generalization and simplification of his work. Okay, so here's what we're going to do. I'll tell you about the algorithmic tasks we're going to study, and then I know that everybody is into quantum, so I'm going to try to black box how quantum fits into the picture. And then I'll tell you about the known non-quantum algorithms for this task, and this is actually maybe the most interesting part, and also something that we didn't do. It's previous work. And then I'll tell you a little bit about how to use quantum to get a faster algorithm, which is the point, and then I'll end with a few open questions. Okay, so the problem that the algorithmic task that we're going to study, it doesn't have like a very clear name. And maybe it's like the planted random KXOR problem, or some people call it tensor PCA. It's kind of like optimizing a low-degree polynomial over Boolean inputs. And it's also kind of related to this cryptographic task of breaking Goldreich's pseudorandom generator. So I don't exactly know the name, but I'll just tell you the problem here on this next slide. Okay, so here's the task. There's a secret Boolean vector called S that's like n bits long, and bits are always going to be plus or minus 1 in this talk. And your algorithm gets like m random clues about what this vector is. I'll say what a clue is later, but like it gets a bunch of clues about S. And so you're probably thinking to yourself, okay, the task is to determine what the secret vector S is from these clues, which is a valid task, but actually I'm going to make the task a little bit simpler to turn it into like a yes or no problem. And so the yes or no version of the problem is going to be like this. So you're either going to be in case 1 or case 2, and the algorithm has to tell which case it's in. And in case 1, it's exactly like I just told you. There's some secret string S, and you're getting like a bunch of clues about it, and you have to, well, you're getting a bunch of clues about it. And in case 2, it's like there really is no secret, and the clues you're getting are just garbage. They have nothing to do with anything. Okay, it'll make a little bit more sense when I say what a clue is, but this is the setup. You're trying to tell if you're genuinely getting a bunch of clues about a secret string or you're just getting noise. Okay, so this is the definition of like what is a clue. So when the algorithm's there, it's like, please give me a clue. Here's what happens. So 4 coordinates I, j, k, and l between 1 and n are chosen at random. And then you basically, the clue is basically the product of S's bits in these 4 positions. Si, Sj, Sk, X, L, which is another bit, plus or minus 1. Except not quite. There's like a little bit of noise. So first, like, it's as though this bit were computed, and then it's reversed. It's flipped to the negative of that with some probability, like 1%. And then the clue that the algorithm receives is like the 4 positions, I, j, k, and l, plus this value b. So it basically learns like some product of 4 entries of S, except it maybe gets the wrong value with probability 1%. Okay? So that's what actually happens in case 1. In case 2, whoops. In case 2, one way to think about what happens in case 2 is that it's the same setup, except you flip to negative b with probability 50%. Which, if you think about it, it just means that b is like a random bit that has nothing to do with like this. And so in some sense, it's like there may as well not even be an S. Like if you're in case 2, what you receive as the algorithm is just like, in one clue, is like a random 4 tuple of indices and a random bit, plus or minus 1. Okay, so you have to kind of tell, the whole task is to tell, like, am I just getting like completely random information, or like, are these Bs like more or less consistent with being the products of 4 input bits in S? Any questions so far?
Are we going to look at the case where S is some specific thing or random? Or what?
Yeah, this doesn't matter too much. If you want, you can also assume that like S is a random string. Yeah.
Y4.
Great, Y4. So, yeah, Y4. Well, the version where like you get, this is 1 or 2, both make sense, but both of these problems are like somewhat easy. And basically this problem becomes quite hard as soon as 4 is at least 3, so as soon as at least 3. But aficionados of this problem also like may know that the problem is a lot easier to tackle when 4 is even. And so the smallest even number bigger than 2 is 4, and so it's like the simplest case that we study in our paper. So for this talk, I'm only going to talk about this version with 4, which is a little bit unnatural, but like in the general paper, we handle the analogous problem for any even value of R.
How many clues do you get?
Great, that's an excellent question, and it's very relevant to the story. So I'll discuss this, I think, now. Okay, so one exercise that you can think about is imagine there's no noise, and like this is 0%, so you just get the product of these 4 bits. Then it's very easy to solve this problem with like, I don't know, basically n clues. And not only that, like you can, if there really is an S, you're in case 1, you can just figure out S exactly. Okay, this is because this is like a linear relation mod 2. Yeah, you're getting XORs here. I'll get to the number of clues in a second, but that's one small thing I wanted to say. Another thing I can say is with the 1% noise, this problem can be very hard. Let's say you only get like a linear number of clues, order n clues, which is enough when there's no noise. With the 1% noise, we basically do not know any non-trivial algorithm for this problem, more or less. So it seemingly takes exponential time as far as we know. And actually, this is why it's like quite interesting and relevant for cryptography, because this is like an example of like a really potentially exponentially difficult problem where it's easy to generate these really hard instances. And moreover, it's easy to generate instances where like the generator like knows like a secret trapdoor solution. So it's a really simple example of the sort of problem that's useful in cryptography. Okay, but getting to your question, this problem definitely becomes more easy the more clues you get. You get more clues. And it's not hard to show. I also call this like a little exercise for you to think about, that if the number of clues is much bigger than n squared being the square root of n choose 4, like the number of all possible clues. If m is that big, then it's also really easy to solve the problem. You can solve it in like linear time. So once you get this many clues, the problem is basically easy. And so then there became some interest in like exactly narrowing this range down to try to understand the trade-off between, let's say, running time and the number of clues you get. So yeah, what if m is smaller than n squared? Can you beat 2 to the n time? So the first paper to tackle this problem was this great paper by Raghavendra Rao and Salil Shram in 2017. And they showed this. So they showed that like basically there's an n to the L time algorithm where L is a parameter, provided m is basically bigger than n squared over L. Well, there's also some polylog n factor. But for example, if L is, I don't know, n to the 0.5, that means if you get n to the 1.5 clues, you can do it in like exponential in root n time, for example. And yeah, as you get closer and closer to like n squared clues, you can get kind of closer and closer to polynomial time. And moreover, this is probably more or less the right trade-off if you ignore this polylog n. So a paper with another Kotari and Mori and Whitmer showed that, gave some evidence that this is the optimal trade-off up to this polylog factor. Okay, but then some people, I mean, partly motivated maybe by this cryptographic applications or other applications, you know, were really interested in the finer grained details of this question. So there's a subsequent paper, subsequent paper by Wham, this is Wine, Alawi, and Montanari from 2019, that showed something like this, that you can succeed in n to the L time provided m is at least n squared over L times 0.7 times ln n. So, you know, they got like one factor of log n here, and they got a specific constant here. Actually, for the purpose of this talk, I totally made this constant up. It's clear that if you look at their paper, you could like spend like 10 minutes and figure out like a very small, pleasant, explicit constant to put here. And I only spent 1 minute, so I kind of like did an improper job of it. But it's like something like this. Maybe it's 0.7. Okay. And so our result is that under the same assumption, you can solve this problem in time that's like n to the L over 4. So this is the Quartic, or fourth power speed up in the title.
What does this quickly is like, are you hiding there, or is that just
this is hiding polylog n factors. This is hiding polylog factors plus a +2 in the exponent. So like, it's only like a fourth power if L is kind of large compared to 2. Oh, I missed a bit of the slide, didn't I? Oh yeah, sorry, this is, I don't know where this was. Another advantage of this paper was not even so much that they got this precise trade-off, but their proof was like way simpler than the RRS paper. The RRS paper, I don't know, maybe the analysis is 20 pages, and the analysis of this could be like 1 page. And in particular, it used this so-called Kikuchi method, which I'll explain later in the talk. But this Kikuchi method has been like very successful recently in like solving lots of problems in algorithms and coding theory and other things. So this was the cool origin story of this Kikuchi method. And yeah, by the way, Matt Hastings also independently discovered the Kikuchi method in his paper. Okay, so as I said, our result is like doing this in time that's better by a factor of 4 in the exponent. Now, there's something funny about this where you're like, oh, Another way you could get an algorithm which is faster by a factor of 4 would be to like just prove a better theorem here where like this was 0.7 divided by 4 or something, and then you could speed this up. But our result, I mean, makes sense despite that, insofar as we show that basically, if ever you use this so-called Kikuchi method to prove a result of this form, like if m is at least this, then you can succeed in n to the L time, then we'll get like a 4th power speedup for whatever you manage to prove. Okay. Let me bring the computer a little bit closer here. Okay. Okay, and let me just say one word about this Quartic speedup, about why you might care, because it looks a little bit funny, 4th power in the exponent. Whoa. Yeah, quadratic speedups or square root speedups of quantum over classical are kind of commonplace. Like for example, this is like a well-known fact. If you have a probabilistic algorithm that succeeds with probability epsilon, then normally you'd be like, oh, run it 1 over epsilon times and then it'll succeed with high probability. And it's like another fact that like Grover's algorithm from quantum means you just have to run it square root 1 over epsilon many times. So in light of this, you get like lots of algorithms that are sped up by like a square root in the running time using this observation. So people are not that excited about quantum quadratic speedups. And some of the people that really are caring about quantum computers are like particularly down on them because of this fact. Like okay, if you have a quadratic speedup and maybe n is like 1,000,000, so you're like, oh, I saved a factor of 1,000 with this quantum algorithm. They're like, yeah, but like quantum computers maybe have or are predicted to be slower than classical computers, like in clock speed by a factor of 10,000. And so like you get this quadratic speed up, but then your computer's a lot slower, so maybe it's not actually good for anything. So I don't know exactly the details, but the people who are into it really think that but maybe like a 4th power speed up actually could genuinely be faster with a quantum computer. So I'm not sure, but the point is it's interesting to find speedups that are better than the sort of typical quadratic speedups. Okay, so that's the story on the task we study. And before I start talking about a little bit about like what you can do with quantum, are there any questions? Yeah.
Is that for not the same for though?
Pardon me?
You had a previous for. That's not. I assume it's not the same for.
Oh, right. Yeah, good. So you mean like the running time speed up was like a 4th root. Yeah, that's not the same 4 as like the clue is about 4. Yeah, good question. It's about 4 product of 4 s values. It's like for any product of some number of s values, it's a 4th power speed up. Yeah, thank you. Okay, so now I'll talk a little bit about quantum to black box what we need. So let me start actually before I get to quantum by telling you about like just another classical algorithms problem, which I'll call the largest eigenvalue problem. And in this problem, you're given like a symmetric matrix A. Let's say it's n by n matrix. And let's assume its entries are between -1 and 1, or they could just be plus or minus 1. And let's also assume it's like sparse, its average, or let's say its maximum degree is a big constant, or at most logarithmic. So you can think of this as like the adjacency matrix of a sparse graph where there's like edge weights that are plus or minus 1, if you like. And again, it's kind of a promise problem where like for simplicity, I'll assume this matrix you're given either has like a really large eigenvalue or a spectral norm, like some eigenvalue that in absolute value is at least 0.9 times delta. Delta is like the largest possible eigenvalue you could have. Or case 2 is that like all of its eigenvalues are bounded in absolute value by 0.1 times delta. And you have to tell the difference between these two cases. So this problem is actually not very hard to solve. There's a fast classical algorithm for this problem that runs in almost linear time in the dimension using, for example, the power method. You just pick a random vector and you start multiplying it by a bunch of times, and very quickly it'll be pointing in the direction of the maximum eigenvalue. And every matrix multiplication is basically linear time because we have like a sparse matrix. Okay, so that's great. What more could you ask for? Let me also mention that for this problem, there's a quantum algorithm that it runs in basically square root n time. And this uses some quantum stuff, Hamiltonian simulation and phase estimation. Let me just say, like, okay, that's great, but this is merely a quadratic speedup. So, okay. Good. Now, let me tell you about a variant of this problem, which maybe is less well known. I'll call the guided largest eigenvalue problem. Same problem. Oh wait, I think it missed a slide. Maybe, Yeah, maybe not. Okay. Okay, so it's the same problem. You're given this matrix, and you're in one of these two cases. But you're also given like one more piece of information which might help you. This is the idea. You're given a so-called guiding vector psi, which is a unit vector which has the following properties. In the case that A has, I'm just going to call this a big eigenvalue, although it might be either a big positive or a big negative. In the case where A has like a big eigenvalue, you're promised that this psi maybe is not like eigenvector that establishes this, but it has like good overlap with the largest eigenvector, or it has like good overlap with the subspace of all the eigenvalues that are bigger than 0.9 delta. And the assumption is that the overlap is at least some parameter gamma. This is a parameter of the problem, gamma. So this may help you. And regardless of whether you're in case 1 or case 2, you get this guiding vector psi. But the case 2 promise is nothing. Like in case 2, psi is just nothing special about it. This is a bit of like a footnote, but I think I missed a slide here. But what we're going to be interested in is the possibility of having sublinear time algorithms for this problem. Yeah, actually, I could have sworn I had a slide about this. Somehow this, clicker is causing me some grief. Let me try a different one. For this problem, a question that we're going to be interested in is whether you can solve this problem in sublinear time. Okay, and how could you solve this problem in sublinear time? You certainly have to have like a randomized algorithm. And you certainly need some kind of like adjacency list access to the matrix A, because you can't just like read the whole matrix. And it's not hard to show that for like a worst case matrix A, it's not possible to have a sublinear time algorithm. But maybe in some average case version of this problem, you could potentially have a sublinear time algorithm. So this is what I went back to this slide I missed, because we are going to be interested in the possibility of solving these problems in sublinear time in the dimension. Okay. Okay. Yeah. So sorry, I did this in a bit of funny order here. So back to this guided version where you're getting this kind of maybe clue about the largest eigenspace, should it exist. Again, if you're going to try to do like a sublinear time algorithm, like you don't have time to even read this whole guiding vector. So you have to assume you have some kind of special access to it. So this is what I mean in the two cases. And for the quantum algorithms, you need that you have a quantum circuit that prepares this vector. But don't worry about this very much. Okay. So let me talk a little bit about this parameter gamma. So if you're just given the matrix A, one thing you could do is just pick a random vector. And a random vector, by randomness, will have overlap with the largest eigenvalue, or eigenvector, an overlap that's like 1 over the dimension. So kind of having overlap like 1 over n is kind of the same as not having any guiding vector at all. So we're kind of interested in the case where this gamma parameter is larger. But one might ask if having this guiding vector can help you. And it's kind of easy to see it doesn't really help with the power method algorithm. The power method algorithm actually starts itself out by picking a random vector and then multiplying A against it a bunch of times. But it converges very rapidly, so that if the starting vector is like good overlap with the eigenspace, it doesn't really especially help you anyway. But perhaps you could do something different. And there's this paper by Garibian and Legal from a couple years ago that kind of introduces this problem in a quantum context. And they gave like a classical algorithm which may be faster. So their algorithm is basically polynomial time in 1 over gamma, the overlap parameter. It's really polynomial time if this delta is a constant, if delta is logarithmic, then this is log n. So let's just call it a big polynomial in 1 over gamma. And so like if gamma, this guiding vector's overlap is quite large, then this could be a fast algorithm. Like if gamma is constant, this would be polynomial time. Sorry, it would be polylog time. On the other hand, if gamma is like just a sort of mildly bigger than 1 over the dimension, then this will not be better. In fact, it'll be worse than the power method. So it's not really any improvement unless gamma is really quite big, like 1 over n to the little of 1. On the other hand, this faster quantum algorithm for finding or understanding the largest eigenvalue has like a very natively like supports like having this guiding vector very well. And there's like a direct relation that's like this. So if you give it this guiding vector with overlap gamma, the running time is basically 1 over square root of gamma. And you can see, by the way, that this kind of recovers the guideless case I told you about before. When there was no guiding vector, I said the running time was like square root of the dimension. And you know, if you have no guiding vector, you could just pick a random vector and it'll have overlap 1 over n. And then if you plug that in here, you get this square root n time. So what it's saying is that like, you know, anything like better than that, like correspondingly helps the quantum algorithm be faster. Okay. So let me try to fit this back into the story I was telling you about earlier. So this was the problem we were studying before, this tensor PCA, a random 4 XOR problem where you get a bunch of clues about this secret vector, or you get just random noise. This WAM algorithm, you know, ran in time n to the L, provided m was this big, and our algorithm is running in time better by a 4th root. And this is exactly because of this guided largest eigenvalue problem, as I'll explain. So how does the WAM paper work? The WAM paper works like this. It takes all the clues it gathers up and builds a capital N by capital N matrix out of these clues called the Kikuchi matrix, K sub L. And the dimension of this matrix is quite big. It's n to the L. And what they show these two facts. That first of all, if you're in case 1, like you're really getting proper clues about a secret string, then this matrix you build will have a largest eigenvalue, which is at least 0.9 times this delta, which is like the sparsity of the matrix. And on the other hand, if you're just getting like random noise, then the matrix you build out of the clues they show will have largest eigenvalue at most 0.1 times delta. And you know, that's their main work. And then once you have that, you can say, oh, so there's a classical algorithm, the power method, that can distinguish between these two cases in time that's basically the dimension, which is n to the little l. And perhaps you can a little bit guess like what we do. So what we show is that in the same situation, not only can you build this Kikuchi matrix that has these large or small eigenvalues in the two cases, moreover, if you're in case 1, you're genuinely getting like good clues about this secret string S, you can take these clues and build a guiding vector which has decently good overlap with the large 0.9 delta eigenspace. And this overlap that's decently good is like 1 over square root of n. And then you plug it into this quantum guided largest eigenvalue algorithm, which had running time 1 over square root of the overlap, and you get 2 square roots on the capital N. So that's the running time is capital N to the 1/4, and capital N is like n to the little l, so the overall running time is n to the little l over 4. Okay, so like somehow like one of the square roots is like kind of the usual square root from Grover algorithm kind of stuff, and like the other square root is by finding this like extra helping guiding vector about this eigenspace. Yeah.
Does the delta show up anywhere in this quantum algorithm?
Not very much. The delta only, it shows up in the running time by like a multiplicative factor of delta, so that's not very big. That's a log factor that I'm hiding in this twiddle in the running time. The main place that it plays a role is in the proof of this fact. You need delta to be at least logarithmic in order for this fact to be easily provable. But I'll explain that
You'll
later.
tell us this construction of the Kikuchi.
Yeah. So in fact, that's exactly my plan now. You know, where I said here originally that I'm going to explain the known non-quantum algorithms for the task, I'm just going to explain this like a Kikuchi matrix and the construction of this matrix from the WAM paper. Okay, so this is not our results or anything, but it's nice to talk about. Okay, so yeah, to put you in mind of what we're doing again, let's go back to this problem that you can forget a little bit about the quantum stuff. Go back to this problem that we are trying to solve. And we're trying to illustrate this WAM theorem, which is like you take all these clues and somehow build like a pretty big matrix whose eigenvalues tell you whether you're getting good clues about a string S or you're just getting random bits. Okay, so this is a reminder of what they are going to do. Don't question me too much here. I'm going to switch to having delta stand for the average number of non-zeros per row and column instead of the maximum. It's not a big deal. And yeah, I'm just restating what they proved a little bit differently. So they're going to make this like capital N by capital N matrix, where capital N is n to the little l, with this sort of sparsity per row and column. And this fact that I told you, they proved that in the case 1, the largest eigenvalue is bigger than 0.9 delta is not very hard. And the somewhat harder thing they show is that once this matrix has large enough sparsity, about logarithmically many entries per row and column, you can get this good bound on the spectral norm of the largest eigenvalue. And it turns out in the construction, delta has this formula, and this is, again, not very important, but it's just if you put these two things together, you see that in order for everything to work, this expression for delta has to be bigger than ln capital N, and capital N is n to the little l, so this is like L ln n, and anyway, you rearrange it, and this is where this like expression comes from, if you pay attention to the constants. Okay, so this is not the most important thing to know about, but this is somehow where this condition comes from. It's because you need to get the Kikuchi matrix to be about this dense. Okay, but let's not dwell on that too much. Now I want to tell you what this Kikuchi matrix is, and there's a lot of steps to building up the definition, so let me go through it. So first of all, I said the dimension capital N is going to be something like n to the little l. Actually, what it precisely is like n choose L. And what this means is we're going to be doing linear algebra over like n choose L many dimensions. And like you think of the coordinates or the dimensions as being indexed by subsets of 1 through n of cardinality L. Okay, so for example, if like W is a vector in this space, then we'll write one of its entries as like W of T, where T is a subset of the n positions of size L. Think of L as like a big constant. And, or if like capital M is a matrix on this space, we'll write its entries as M, T, comma, U, where T and U are subsets of 1 through n of cardinality L. Okay. Okay. So towards defining this matrix, let's say we have a string S, which is like, the secret probably. I'm going to define from it a new plus or minus 1 vector in this big dimension, and choose L, which I'm going to call, I think this is like S dot. The S dot entry corresponding to a subset T of cardinality L is maybe the most natural thing. It's the product of Sj's entries for J in this set T. So it's also a plus or minus 1 vector in this larger dimension. It just encodes all the sort of T-fold products of entries of S. Okay. And I need to make one more definition. Fix some set C of indices of cardinality 4. And the C is going to be like, the IJKL that you might get in a typical clue. And I want to define a matrix in this big space, which I'm going to call M sub C. It depends on this fixed size 4 set, C. And it's a 0, 1 matrix. It's symmetric. You put the 1 between row S and row T and column U. These are subsets of size L. If their symmetric difference is this specific set C. So L is pretty big, so these T and U are like pretty big sets of coordinates. And you connect them if their symmetric difference is like this really small set C of size 4. So they overlap on like all but 2 entries, and then T has 2 distinct entries and U has 2 distinct entries, and those 4 entries together are C. So this is actually an adjacency. Another way to think about it, this is an adjacency matrix of a graph. It's a graph where the vertices are all the sets of size L from an n size universe. And it's also a perfect match, or not a perfect matching, it's a partial matching. Because every vertex here has some set of size L, and it might have like no edge. Okay, when does it have an edge? A set T has an edge if T symmetric difference with C is another set of size L, which doesn't always happen. It only happens maybe if C overlaps with T on exactly 2 elements. Right, so this is, depending on C, this is the adjacency matrix of some partial matching on this big set of vertices. Okay, we're still getting towards defining this Kikuchi matrix. Okay, last thing to think about. Okay, S dot is this vector. So this vector, it's got plus or minus 1 entries. You can think of it as a labeling of the vertices by plus or minus 1. Because these vertices are the size L subsets of n. So it kind of looks like this. And now I'm going to ask you a question. I know it's late in the day, but I will ask you. If you do this, then I claim actually that if you look out over every edge in this graph, and you look at the product of the labels endpoints, it's actually always the same. In this illustration, it's always minus 1. And what is that same value that it always is? Can somebody calculate in their head? Yeah, exactly. It's the product of S's values for J and C. Because if this is an edge, if this is T and this is U, this labeling is like the product of all the things in S and T. It's the product of all the things in U. For all the ones they overlap on, you'll be producting that plus or minus 1 value twice. So it'll cancel out to nothing. And the ones left over that you actually do retain the product for are the 4 entries in C. Okay, so all these edges will have the same endpoint products, and it'll exactly equal this product of S's values on C. Let me call this bit B sub C. Okay, final step before I'm ready to, like, this sort of motivation for defining this. Final step is I want to think about this quadratic form, like the quadratic form of like S dot with this adjacency matrix. Okay, so what is this quadratic form of S dot with this adjacency matrix? If you look at this definition of the matrix here, you basically sum over all entries in the matrix that have a 1, so it's all sum over all T and U, whose symmetric difference is C, of S dot's entry for T and for U. And we know what that is. That's exactly this BC. So we just count this BC like many times, like 1 time for each edge in the graph. Okay, if you want to be really formal, it's sort of like 2 times the number of undirected edges, or just the number of directed edges in the graph. Don't worry about this factor of 2. So like this is the same value for all sum n here. So this quadratic form is this sign BC times however many edges there are in this fixed partial matching. Okay, whoops. So let's write this like this. And then this is just plus or minus 1, so I'm going to put it in here. Good. So actually, okay, this is finally all to say that, you see, let's say you're now actually in the problem we're trying to solve, and you're given some clue, like this is C, and this is some value B. And this B is usually equal to this BC, 99% of the time. So what this means is every time you're given a clue that looks like this, the quadratic form of like the lift of this secret string S with this matrix B times MC, it's either plus or minus the fixed number of edges in this matching. So like with the plus being 99% of the time. So it's usually plus the number of edges, and occasionally it's minus the number of edges. So like basically like this is a really great vector for quadratic forming with this matrix that you get out of the clue. So now this is the definition of the Kikuchi matrix motivated by this. You just take all the clues you get and like sum up this matrix. This is plus or minus this fixed partial matching. And again, this is like sort of like a plus or minus sum of a bunch of partial matching. So it's like maybe minus this partial matching, plus this partial matching, plus this partial matching. So you get like a graph with plus or minus edge weights. And what we've shown is that after you get m clues, most of the time this quadratic form of S dot with like one of these summands is giving you plus the number of edges in this partial matching. So like 99% of the time you'll get a plus, and 1% of the time you'll get a minus. So basically you'll get 0.98 times the total number of matchings in all the clue graphs. And what I'm getting at here is that, like, as you'll kind of see, this S dot, which is some reflected from the secret vector, is like, it's like a really good, I don't know, eigenvector, but it has a really good quadratic form with this matrix that you've constructed. That's sort of the idea. Let's do a little bit more arithmetic. So I'm just going to divide by capital N, which is also the squared length of S dot, because it has all plus or minus 1 entries. And then this looks like the average degree in the graph. So after m clues, if you just like superimpose all the partial matching graphs you get, this ratio, quadratic form ratio, is around 0.98 times the average degree. And therefore, like, that shows that, like, first of all, this matrix has an eigenvalue that's at least 0.98 times delta. And moreover, it's like kind of witnessed by this vector S dot. Okay, and this is like basically half of the analysis of this WAM result. So remember, this is what we basically just showed, that when you're really properly getting clues about some unknown secret string S, you build this matrix K sub L. Pretty much all the time, its largest eigenvalue is going to be, well, even around 0.98 times delta, so at least 0.9 delta. Good. So you might be saying to yourself, okay, you defined this matrix, and it took a long time, and you established this. Like, this is probably going to take even longer time. But actually, I'm going to dispatch with this like harder part in like a very short amount of time. And yeah, here's the gist of that. So this Kikuchi matrix that you build from the clues, it's like some sum of like these matching matrices times a sign, plus or minus 1. And now let's imagine you're in case 2, where the C's are random, but also the B's are just random plus or minus 1 values. So then, basically, this becomes like the adjacency matrix of like a graph with edge signs. And it's basically like a randomly edge-signed random graph of average degree delta. And there's many theorems you can prove. If it were like a truly random graph of this average degree and with random edge signs, there's like classical kind of theorems saying it has like all small eigenvalues. Maybe the most efficient way to show this, if you don't mind losing a log factor, is to use this matrix Chernoff bound, which more or less you can apply here by virtue of the fact that these B's are just random plus or minus 1 signs. So that's basically all I'll say, but like once you set it up and you know this, cite this matrix Chernoff bound, then you can show this in, I don't know, just by almost immediately applying this bound. Okay, and the reason, by the way, if you're an aficionado of this stuff, you know the matrix Chernoff bound has some extra factor, which is like log of the dimension. And that's kind of why you need the average degree to be at least as large as log of the dimension for this to kick in. It's a bit of a technical detail. Okay, any question about this?
You said that this one was harder, like, I mean, you're skipping a lot here, but what is the hard part of this?
It's actually, in some sense, not harder. I mean, well, okay, this one you have to, like, let's say, appeal to a powerful theorem or, like, suffer by proving it with some other trace method or something. Here, it kind of almost follows by the setup of, it follows by the definition of the matrix. So we took a lot of time to define the matrix. That's why maybe it seemed like a long time, but here, at least you need some non-trivial theorem.
Are you going to explain where Kikuchi comes from? Like,
Oh, Kikuchi is like the name of some physicist, and like the WAM paper, they said they were inspired to construct this matrix. I'm sorry if they're like physicists who like know this better than, they were inspired to construct this matrix by considering this notion he invented called Kikuchi free energy. Yeah. Then I kind of know that, I don't know if I should say this out loud and on camera, but like I kind of know that like many of these subsequent papers that use this Kikuchi matrix method, they really took enjoyment in calling it the Kikuchi method because it was like a catchy name. Like instead of calling it like, that method where you construct the matrix with the subsets and so forth, no, they're going to call it's the Kikuchi method, and that has a catchy name. Right. Okay, so we're almost done. yeah, this last thing I have to tell you is about, okay, the point of the paper, this is all previous work, is to like get this, use this quantum trick with the guided eigenvalue thing to get this fourth power speed up. So let me say something about that. So kind of the plan hopefully makes sense. This is some like recap of what was going on. So we talked about this Kikuchi matrix that has like basically n to the L rows and columns. And we've got this setup where, they prove that, okay, in case 1, it has this large eigenvalue. In case 2, it has only small eigenvalues. But moreover, now we're going to remember that in case 1, it's not only that it has a large eigenvalue, but it's kind of witnessed by, well, the secret vector extended or lifted into capital N dimensions. And what we want to show is that we, or the quantum algorithm, can moreover take these clues and not just construct a Kikuchi matrix from them, but also construct like a guiding vector which has a little bit of decent overlap with this large eigenspace, when you really are in case 1 and there's a secret vector that you're getting actual clues from. And this is how, if we get this to be 1 over square root of the dimension, then this is how we get this running time that's better by a factor of 4 in the exponent. So now we can actually simplify the parameters somewhat. So first of all, you actually only need to remember that m is vaguely around n squared. And this capital N is like n to the little l. So this said 1 over root capital N before. And I'm just saying, just think of it as n to the minus l over 2. Moreover, I'm going to just explain to you now that technically, instead of showing that this guiding vector we construct has good overlap with this eigenspace, I'm just going to show it has good overlap with the one-dimensional subspace through S dot. And morally, this is the same thing because we kind of showed that like this eigenvalue being large was like witnessed by this S dot. Mathematically, if you think about it for a bit, it's actually kind of cheating because you don't exactly know that S dot is in this subspace. It just has maybe some decent overlap itself, and then having overlap is not transitive. Like if this has good overlap with this, and this has good overlap with this, it doesn't mean this, but never mind. Let me just show you this, and that's the idea. So yeah, I'm going to show you that there's a way to convert the clues into some vector that has some little bit of correlation with this S dot. Finally, there's only one slide for this, but I have to remind you, what is overlap again? It's basically the square of the inner product between these two vectors. Except when I defined it, I assumed they were both like unit vectors. But now it's inconvenient for me because I don't want to introduce normalization factors, so I'll just divide by the lengths down here. So this is the formula for overlap for two general vectors. Okay, so the idea fits on one slide, which is good because we're almost towards the end of the time. This is what we want to do. We want to take these clues, of which they're about n squared, and construct some vector psi that has pretty okay overlap with this S dot. So one more piece of notation, sorry. For a general set C, I'm going to let SC, superscript C, denote this thing, the product of the Sj for j in the set C. We called this by a different name before, but I'll call it this now. And I'll mostly think about C of cardinality 4, but also some other Cs. So for example, what is this S dot vector? Maybe you forget. This S dot vector is this vector of dimension n choose L, where it's like the vector of all the ST values when T has cardinality L. Okay, and that's the thing that we're trying to be a little bit correlated with our guiding vector. And each clue more or less tells you one SC value for C of cardinality 4. I say more or less because like 99% of the time it really tells you this SC value, and 1% of the time it tells you the negative of that value. But as you'll see in a second, it doesn't really matter. That it's enough that like most of the time it's giving you a correct value. Okay, so here's literally the only idea. Imagine you took, for example, let's say 2 clues that you got, and some C1 and C2, and you just and a bit for each of them, and you just multiplied the 2 bits together. That would probably be equal to S of C1 union C2, at least as long as C1 and C2 didn't overlap. And then you could multiply in another S clue, SC, and in that way you could build up like a pretty good idea of like these S values for bigger sets. In particular, like let's say you took any collection of L over 4 clues that you got and multiplied the associated B values together, assuming these clues were all disjoint, this would more or less, except for the error, this would more or less tell you one of the ST entries in this S dot vector. Now, it's pretty much, if you check the parameters, like almost all the collections of clues will be disjoint. So pretty much almost every like L over 4 tuple you can multiply together in this way, and the error doesn't collect up too much. So by doing this, you can kind of learn, like, more or less, M choose L over 4 entries of S dot. And M is kind of like n squared, so this is like n to the L over 2. So by doing this, you can take the clues and kind of more or less figure out n to the little L over 2 entries of S dot. And that's a decent number. I mean, S dot's dimension is like n to the L, so it's like square root dimension many entries you've kind of learned. And now it's a calculation. So let psi just be the vector in this large space n choose L with -1, 0, and +1, where you put in a -1 or a +1 for all these entries that you kind of learned by combining clues, and 0 if you didn't learn anything about that particular entry T. And these plus or minus 1 values are pretty much the entries of S dot. So yeah, now we can just calculate all these expressions. So psi's inner product with itself, it has about n to the L over 2 many non-zeros, so that gives you n to the L over 2 here. Psi's inner product with S dot, like the point is that like whenever psi has a non-zero entry, it's the same, well, pretty much, as the S dot entry. So this is, inner product is also like n to the L over 2, so when you square it, you get n to the L. And this S dot just has n to the L many plus or minus 1s in it, so that's this n to the L. And then you plug it in up there, and it works. You get n to the L in the numerator and n to the 3/2 L in the denominator. Okay, so maybe even the exact calculations are not so important, but the point is like, yeah, you can take the clues and learn, or approximately learn some of the entries of this S dot thing. So you get like a little bit of overlap with this, biggest eigenvector, or a proxy for the biggest eigenvector. And that somehow really helps the quantum algorithm in a way that it doesn't really help, seemingly, the classical algorithm. Okay. Okay, for the hardcore quantum people, I actually have to like put up this fact too. There's actually one crucial thing that I'm slipping under the rug here, which I'll now tell you, but if you don't want, you don't have to pay attention to this. The point is, like I just told you, we can construct this guiding vector that has like good overlap. Its dimension is like n to the L. And we're trying to get like a running time that's like n to the L over 4. So like you don't want to like literally write this vector down. You don't even want to like literally just like write down its non-zero entries, because there's still n to the L over 2 of them. So you need to like be able to like kind of implicitly describe, or what you really need for the quantum algorithm is like a circuit that prepares this guiding state in like much slower time, and faster time. And kind of by a miracle, there's a way to do this. So like, if you first prepare this state chi, it's like an unnormalized state, but don't worry about the normalizations, chi of dimension n to the 4th, where you just like write down basically all the clues you got. Like if you got a clue, you write down plus or minus 1, and you leave all the clues you didn't get as 0. You can construct this state like brute force in like, I don't know, n squared time. It's only of dimension n to the 4. And then you just construct this state, and then you construct it again, and then you construct it again, and you construct it again, like L over 4 times. So it takes, n squared time times L over 4, which is basically n squared time. And the rules of quantum mechanics say that what you get is this product state. And then if you think about it, this product state, which is like all sort of the L over 4-fold combinations of the clues, is exactly the guiding state. So luckily, not only does this guiding state vector work, but you can construct it very efficiently. It has this like kind of implicit representation that's very simple. Okay, that's a bit of a footnote. Okay, so I have one more slide. It's just about open questions. So yeah, in this paper we actually used this guided largest eigenvalue problem to get like a faster algorithm for some interesting classical task in the field of planted inference. And it's an interesting problem, and it actually, in some sense, it's kind of complete for quantum computation if you define it appropriately. So there's some sense in which is like, arguably this is the only thing you could do with quantum computation. So, if you're interested in getting, quantum speedups or better than quadratic quantum speedups for some classical problems, then maybe you can try to fit them into this guided largest eigenvalue task. The other thing is this. So, I've given this talk before, and people always are say the following to me, yes, you gave a faster quantum algorithm for this classical problem, but maybe there's a faster classical algorithm. So, what if there is? And I did say that, okay, if the faster classical algorithm follows this Kikuchi matrix method, then however fast it is, our methods will make it, quartically faster. But, people are but maybe there's another faster algorithm. Maybe you should use, some tensor circuit somethings, or maybe you should use some sampling something. And I was always, a little bit annoyed, because I was hey, do we have to do that? We came up with this quantum algorithm. It's not our job to also try to come up with a better classical algorithm. If you think there might be a better classical algorithm, please try to find it. You can have a nice new result that improves upon, this 5-year-old paper. But okay, I was all right, fine. So eventually I'm okay, we'll try to think about it. So yeah, now with some other colleagues, the same colleagues and some more people, we're trying it. We're going to see if there can be a faster classical algorithm, not via the Kikuchi method. And I guess I don't know whether I'll be happy or sad if we succeed, right? If we succeed, then we get this faster classical algorithm, but then maybe the quantum thing is only a quadratic speedup. If we fail, then I don't know what we'll do. We can add a sentence to the paper saying we tried really hard to get a faster classical algorithm and we couldn't, so that's our evidence. But anyway, that's what we're working on now, and that's where I'll stop. Thanks.
So just a reminder that if you have a question, do raise your hand, and I'll bring the mic over to you, because otherwise your question wouldn't be recorded on camera.
So sorry if I missed it, but could you say a little bit about how this guided max eigenvalue algorithm works?
The quantum one?
Yeah.
Yeah, so it's the question about how the guided max eigenvalue problem works. So first thing is the problem is about trying to decide if a symmetric matrix has a large eigenvalue or a small eigenvalue. Quantum, we really like unitary matrices rather than symmetric or Hermitian matrices. So if you could just take this matrix and make e to the I times that matrix, that would convert it into a unitary matrix, and there'd be a clear relationship between the eigenvalues. And this subroutine called Hamiltonian simulation does exactly this. So people worked on a lot, including people here at Waterloo, and gave efficient algorithms if the matrix is sparse, basically, for sort of implementing e to the IA, given some kind of adjacency list access to A. So that kind of converts the problem to trying to understand if a unitary has a large eigenvalue or a small eigenvalue. And for this, there's another classical quantum algorithm called phase estimation. The simple version of phase estimation is you have this unitary. If you also have an eigenvector for it, then this phase estimation algorithm will just tell you the eigenvalue of this eigenvector for this unitary. But it has an additional property, if you think about it, that if you just put in any old vector here, it kind of tells you a random eigenvalue of the unitary. And it tells you about each eigenvalue with the probability equal to the overlap between the input vector and the associated eigenvector. So if your input vector has a reasonably large overlap with a particular eigenvector, then phase estimation will have a reasonably high probability about telling you about that eigenvalue. So those are the ingredients that you put together to get this. And the higher the overlap is, the larger the probability that phase estimation will tell you about that eigenvalue.
Other questions?
So this guided eigenvalue problem, it kind of reminds me of some, I guess, a stream of literature which is algorithms with machine learned advice. So you're getting some advice about the eigenvalue. So, do you know if there's any sort of work in classical algorithms for okay, maybe not the power method, but something else that...
That's a great question. Now that you mention it, I also see how it reminds one of that. I don't know about classical algorithms like this. I think it is related to the quantum motivation that people had for this problem, where they're basically trying to solve this largest eigenvalue or estimating the energy of a Hamiltonian problem. And they imagine that maybe some chemists use some heuristic to find like a state that's maybe close to optimal. And they're not sure where that came from, but like once they have it, they can get like a better improved algorithm for estimating this largest eigenvalue in their terms. But it does remind one, one could imagine, one should possibly imagine like a similar scenario maybe in classical algorithms. So I don't know of one, but it makes sense.
So I have a question which might be equally annoying as the one about classical algorithms. How about faster quantum algorithms? So there are two places I saw, where this Quartic and the, thing might, due to which that might be optimal. One is phase estimation, and the other one is this overlap of the vector. It looks like neither of them could be improved. I think phase estimation is optimal.
Yeah, so the ingredients, like phase estimation can't be improved. I guess the natural question is, could you figure out like a guiding vector state that has even larger overlap? That would immediately give you a faster algorithm. On one hand, we don't know how to do this, but on the other hand, there is like some room to try things. Like maybe you don't have to use this Kikuchi matrix. Maybe you could do some other matrix, and you'll be able to do a better job of finding a guiding vector for it. Yeah, we don't know. This is the best that we could do.
Before we thank Ryan again, a reminder that there's a reception just across the hall, so please feel free to join us there. And thanks again, Ryan, for a wonderful talk.
Yeah, thanks.